Hello! Welcome to this talk about gravity, where we are going to talk about the laws of gravity and a few equations and how you can use those to derive a few things as well. Buckle up! Isaac Newton shocked the world, not so much by explaining that things fall, because everyone knew that things fell to the ground, but he figured out that the same force that causes things to fall also caused all the planets to stay in orbit around the sun and the moon to stay in orbit. And that mathematical law that we put here is this: that the force is going to be proportional to the product of the two masses. So if you multiply the mass of the Earth by the mass of, let's say, a space station that's orbiting around it, then it's inversely proportional to how far away it is. That equation is going to be big G, the mass of one times the mass of another, over r squared, where this is the distance between them. G is a constant, and that G is a crazy small number, 6.67 times 10 to the negative 11th over per kilogram squared, Newton meter squared per kilogram squared. And this is such a small number that unless you have incredibly large masses, the force of gravity is very, very, very small. Now, this force works for both objects. Let's say we've got the Earth here, and I've got some little satellite thing that's in orbit. There is a particular force pulling down on the satellite. There's the exact same force pulling on the Earth this way, by Newton's third law, and by this equation. But you don't notice that force on the Earth because the Earth is so incredibly massive. You can also say that this equation is going to be true not only for massive things like black holes and moons and galaxies, but even you and the person sitting next to you have a force of gravitational attraction between you, but it's so tiny that you don't notice it. Gravitational field strength is slightly different than what we were discussing before as a gravitational force, and we draw gravitational field strength always as going inwards towards the object that has the mass. Wherever you have a higher concentration of field lines, then that is going to be stronger. Out here, where there is less of a concentration, then that has to be weaker. So if something is in orbit high above the Earth, it's in a slightly weaker gravitational field. Keep in mind the gravitational force doesn't disappear just when you are up there in orbit, which is some people think is what makes astronauts weightless, which is not true. They're in free fall with their spaceship, which is why they appear to be weightless. But there is still a force of gravity on them. If we had a smaller object, like the moon, then we would not draw as many gravitational field lines because its gravitational field strength is not as strong as that of the Earth. Now, a definition that you need to know for gravitational field strength is that it's measured in force per unit mass. And the equation then, which we usually use the small g, which should look familiar, as the force of gravity divided by the mass of the object. Now, you should know that this is a vector. It's always directed inwards to the planet, and the units, you can probably guess, based on the equation, are Newton per kilogram. Now keep in mind, this is the same as the units of meters per second squared, because this is actually also free fall acceleration. If you work out the gravitational field strength on the surface of the Earth, it is 9.8 meters per second squared. Let's try a sample problem. The International Space Station is far from weightless. It's the force of gravity that keeps it in orbit. In other words, that's its weight that keeps it in orbit. Use Newton's universal law of gravitation to find out what the weight of the space station is. Pause it, attempt to solve. I hope you realize that you have to add not the radius of the Earth to the altitude of the satellite, because that does make the acceleration a little bit weaker up at that altitude. And keep in mind, it's not a very high altitude. It's only 400 kilometers above a very massive Earth. So hopefully you got your combined radius and altitude of the 6.8 times 10 to the 6th meters, and then you get a significant force, it's not weightless, of 3.6 times 10 to the 6th newtons, or 3.6 million newtons, which is a lot of force on it. Now, what I'd like you to do is compare this weight to what would the weight of the ISS be if it were sitting on the Earth's surface. Pause it, see if you can figure that out. Now that is pretty simple to do, because you just do m times g, 9.8. And if you do that, you get an answer that is something like 4.1 times 10 to the 6th newtons. So while it's not weightless up here, it does weigh a little bit less than it would if it were sitting on the surface, because the gravitational field strength is weaker at that altitude. It turns out, if you know the radius and the massiveness of any planet or moon, you can figure out what its gravitational field strength is going to be. And we're going to derive the equation for that here, because it's not very difficult. So let's say that we want to derive that equation, which is also not only the field strength, but also the free fall acceleration on that planet. So let's say we've got small g, and we know that it is F over m. We're going to plug in, pause this, see if you can get it before I do. We plug in universal gravitation law by Newton of big G m over r squared divided by this m here. This is going to be the mass of the object. Here it's also the mass of the object. Those go away. And we get the very simple equation of this here. And then you just plug in the mass of your planet. The distance between the two objects would be the radius of the planet, assuming that you're standing on the surface of your moon. And then you can figure out gravitational field strength, which is the same thing as the acceleration due to free fall.